Great, so first section, this week we're going to pick up where we left off in section 1.3, talking about functions. We're going to start by looking at a function and finding its domain and its range. Okay, so kind of a review. We've done this before, but good problem to just refresh how we find domain and range. All right, so anybody remind me on the calculator, how do I get to the screen where I can type in a graph? Hannah?
Hit the y equals.
Yep, hit y equals. And now I'm going to type in exactly what I see here. 16x minus x cubed. Does anybody remember what I said about how many twists and turns the graph can take based on this highest exponent? It's not quite this exponent, but that exponent tells you.
And it's that exponent minus 1?
Yeah, it's one less than that. So this graph could twist and turn up to 2 times. I'm not saying it will, but I'm saying it could. Okay, so I'm going to hit graph. And we'll take a look at what we've got. Okay, Alex, is that a good window? No. All right, it's not a good window because I'm cutting off parts of the graph. I think it's turning, but I can't see it. It's off the screen. Somebody tell me which of my 4 values, x min max, y min or max, do I need to adjust so I can see what's happening? Well, John?
I would change your y min and your y max.
Yeah. I don't know exactly how high or low I need them. Let's try... let's just try negative 40 to 40. If we still can't see the turns on the screen, we'll adjust it again. Oh, that's perfect. All right. So since this is a cubic, I can see both of the turns on the screen. Nothing else is going to happen with this function. Okay, what you're seeing on the screen is all that it's ever going to do. This right side is just going to keep going down. Left side is just going to keep going up. All right, so we've got a picture of it to help us out. And now let's see if we can figure out the domain and the range. Okay, if you need the x min and max, I can just get those for you. Right there. Okay, that was negative 10. All right, so domain. So the domain are the numbers you are allowed to plug in for x. If you want to think of it visually, it's how far to the left and the right that graph is going to go. Okay, how about Jack? What kind of numbers are you allowed to plug in and multiply by 16? All right, let me ask it differently. What kind of numbers are you not allowed to multiply by 16? Like if you typed in 16 times something and you hit enter, your calculator would, screen would crack or something.
Real numbers?
You can't multiply 16 by a real number?
You can't put imaginary numbers.
Yeah, okay, so yeah, real numbers, right? All real numbers. You can multiply any number you want by 16. Okay, so there's no restriction there. Very good. How about cubing a number? What kind of numbers am I allowed to raise to the 3rd power? Well, Fred? Yeah, you can raise anything you want, any number to the 3rd power. You'll never get an error. Okay? So the domain here is all real numbers. Okay? You're never going to divide by 0. You're never going to take the square root of a negative. Those are the 2 things you have to be careful with. All right. So negative infinity to infinity.
Isn't it the same with the range too?
Well, let's take a look at it. So the range now is how high and low the function is going to go. And yes, the function will go down forever on the right side. It'll go up forever on the left. And it's connected. So if it goes down forever and up forever, and it's connected, it must hit everything in between. Just because a graph goes up and down forever doesn't always mean it's connected, though. if you had something like, let's say a graph that did this, and a graph that dropped off like that, well, it might go down forever, and it might go up forever, but there's this gap in the middle. It's not hitting everything in between, right? So you got to be careful when you look at the range to make sure, does it really hit everything in the middle? And here it does. Okay. It is connected. Any questions on how we figured out the domain and range of them? Okay, so domain are your x's. Those are the numbers you're allowed to plug in. Y is your range. Those are the answers that you get when you plug in your x's. All right, let's try this one. I don't think we did do the swimming pool problem yet? Did we do that? No, okay. So we have a rectangular pool. Okay, and this pool has dimensions of 30 by 50. Okay, what we're going to do is put a sidewalk around the pool, and the sidewalk is going to be the same width all the way around the pool. Okay, and we'll call the width of that sidewalk x. Okay, one thing we do know about the pool is that the sidewalk is it has an area of 600 square feet. Find the width of the sidewalk. All right, so they've given us a lot of different information here in written form. I think this kind of problem lends itself to a certain approach to solve it, make it easier to see things. Does anybody have a thought what we might want to do in this problem? Not even anything algebraic yet. Not even asking for like an equation or anything like that. Just something to maybe look at this information in a different way rather than the way it's here. Yep. Okay, so I agree. We're definitely going to find the area of the pool eventually. Even before we do that. Yeah?
Can we draw it?
Yeah, let's make a picture just to visualize all this stuff so we don't have to look at all the words. And maybe the picture will help us to get an equation which is going to involve finding the area of the pool. All right, so I've got my, basically it's going to be a rectangle within a rectangle. Okay, so I got my pool. I got a sidewalk around the pool. What did they say the width of the sidewalk was?
600.
X. Yeah, I don't know the width. Okay, so this is x. That's the width all the way around the pool. They did tell me the dimensions of the pool. It's 30 by 50. What else do I know? The area, I know the area of the sidewalk is 600. I can just kind of squeeze that in right there. Okay, and was it, Adrian, did you say earlier we could find the area of the pool? Yeah. What's, we didn't talk about it, but what's the formula for the area of a rectangle?
Like times width.
Yeah, so we just got 30 times 50, 1,500. And that's measured in square feet. Okay, so that's this whole area here. That's pool. So how could I find the area, or how could I set up a formula to find the area of this strip around the edge if I knew the area of these other two rectangles? But Ryan, any? I want to find the area of this formula for the area of this border region of this sidewalk. and I can figure out the area of this big rectangle and the small rectangle.
Subtract the small rectangle area from the big one.
Yeah. So the area of the sidewalk, which I know, I can put a number in for that in a second, is going to be equal to the area of the big rectangle minus the area of the pool, or the small rectangle. Okay, now let's fill in what we know. Okay, area of the sidewalk. Yep, that's 600. Now I need the area of the big rectangle. So that's length times width. Okay. What's the length of the big rectangle? And again, this won't be a number. Okay, so the length of the big rectangle that's part of it. So x is from here to here. Actually, you know what? Let me do that in a different color. Okay, so that's x. What else? We got a little bit more. All right, what do you get if you add 2 x's together? 2x, so that's that. X, x, and what else?
50.
And 50. So if you add x, x, and 50, that's the length of the pool. Okay, 2x plus 50. I'm sorry, that's the length of the pool and the sidewalk around it. Doing kind of a similar idea, can anybody tell me the width of the big rectangle? About, Curtis, tell me the width.
X.
Yep. You got
Or
x.
2x and plus 30.
Yep. So you got x on the top, x on the bottom, plus 30. Exactly what he just said, 2x plus 30. And if you take the area of that big rectangle and then subtract the area of the pool, we will have the area of the sidewalk. John, what's the area of the pool? 1,500. We had that earlier by doing 50 times 30. Okay, so now we solve that equation, and then we have our answer. All right, so I've got 600 equals, what do I have to do here? Yeah, some people call it FOIL or double distributive property, whatever you call it. So Hannah, can you help me do that? What's 2x times 2x?
And it's 4x.
4. Yep, good. 4x to the second. How about 2x times 30? Good, 60x. I'm just going to put that here for a second because I'm going to combine it with something else. Austin, what's 2x times 50? 100x. And can you add those up for me? 160x. And lastly, 50 times 30, I already did that earlier, gives me 1,500.
So that's the 1,500 and negative 1,500 cancel each other out.
Yeah, those cancel out. And now I'm just left with this. What kind of equation is this? Especially because of that exponent. Anybody remember what it's called? Yep, that's a quadratic equation. So anytime we want to solve a quadratic, whether you're going to factor it, use the quadratic formula, or complete the square, generally the first step is get it equal to 0. And in order to do that, I'm going to subtract the 600, bring it to the other side. Now, when you solve a quadratic, you don't get one answer usually. How many answers do you get? 2. So chances are one answer is going to be positive, one is going to be negative. Just remember what x is. It's length, it's width. Okay, it's a dimension. So can't be negative. Right. So one of the answers when we solve this, however we solve it, probably won't make sense. And one will. Right. I think the easiest way is to probably use the quadratic formula, but I can make all these numbers smaller. Does anybody notice a common factor?
4.
4. So divide everything through by 4. It just makes the numbers a little smaller. Okay, and now we're going to use quadratic formula. Okay, so first thing I like to do when I use quadratic formula, just identify A, B, and C, and then plug it all in. How about Jacob? Can you tell me here what A is?
1.
Yep, it's the coefficient of x squared. It's not written there. It's invisible, but it's a 1. James, how about B?
Is it 40?
Yep, 40. And Sam, how about C?
Negative 150.
Right, negative 150. All right, and now I need my quadratic formula. Does anyone remember how that starts off? Yeah?
It's actually was negative b plus or minus the square root
All right, let me go. Okay, so you have negative b plus or minus the square root of
of b squared
b squared,
minus 4ac
4ac, okay?
2a.
All divided by 2a. So I plugged things in as he said it. Okay, any questions on that?
Where did you get the 16 from?
So that's the b squared.
Okay.
I did 4 times 4 in my head was 16, and then I just added 2 zeros on it.
Oh.
40 times, to do 40 times 40. All right, so looking at what's under the square root, I notice I'm subtracting a negative. So whenever you subtract a negative, it becomes a positive. What's 4 times 1 times 150? Yep, that's 600. And 600 and 1600 is how much? 2200. Now, can I divide everything by 2 here?
Yes. Yeah, 40 divided by 2 is 20, and 220, or 2,200 is 1,100.
Okay, I agree with your arithmetic. If you do what you just said, that's what it comes out to. But,
Square root of 2200.
right, that's not 2200, it's the square root of 2200. So we can't divide this by 2 because it's under the root. Okay? So just leave it, and at this point, let's, we're just going to round the square root of 2200 off. 46.90. I say 46.90.
9.
Now, at this point, I have the 2 answers. I have the plus and I have the minus. Does anybody see which one doesn't make sense?
The minus.
The minus. If you did negative 40, take away 46, that's negative 86. Divide by 2. Algebraically, it is an answer, but in terms of the word problem, if you use common sense, it cannot be negative. So, we only have one answer. We have negative 40 plus 46.9. Negative 40 plus 46.9. And now divide by 2. It's 3.45. About. Feet. That's the width of the sidewalk around the pool. Any questions on that? Okay, now I still have to set up this equation, but I didn't have to go through all this algebra. I could have stopped right here and plugged this in on my calculator. Okay? If they ask you to do it algebraically, then you have to continue on the way we did. If they said solve using a graphical method, I'll show you how you can do that, and you can always double check your answer this way. So type it in just the way it is right there. 4x squared plus 160x minus 600. Now normally I don't know where to set my mins and maxes, but I already know the answer to the problem. 3.45. So in this case, I know x doesn't have to go above 3.45. I'm not worried about negatives, okay, anyway. Not worried about negative width, not worried about negative area. Right, so let's just set x to, let's just go up to 6. Because we know 3.45 is going to be before 6. And we're looking for where this equation equals what number? 0. Okay? So we're looking for where x is 0, which happens right where I just clicked. Okay, so what I can do, we might have done this before, is do second calc 0. Pick a point somewhere to the left of my root. Okay? I know I'm to the left of my root. I'm at x equals 3 right now, even though I'm off the screen. I'm going to hit enter. It says pick a point to the right. Eventually, you'll see the cursor come on the screen. There it is. Now it's going to look in between those two dotted lines for where it hits the x-axis. Because that's where x is 0, where it hits the x-axis. And it says the answer is 3.45. Okay. Exactly the same answer that we got using quadratic formula. Mm-hmm.
What fine did you have to say if you get those numbers?
To get the 0,
Yeah.
you press second calc 0. Okay. And then you have to pick a point somewhere that's below your root. Pick a point somewhere above your root. To the left and to the right. And then do a guess. And you'll get 3.45.
Okay.
Okay, if you have any questions, or if it's not, if you're having trouble, you can always just ask me at the end of class. I can come over and help you out. Okay? I don't care which way you do it if the directions don't tell you to do it a certain way. Do it whichever way you want. Okay, any questions on that? All right. Okay, so last couple things in this section. Okay, they talk about what's called projectile motion. Okay, so that's basically if you think of an outfielder throwing a baseball. Okay, that's projectile motion. Okay, throwing it in towards the infield. Okay, and we can model the height of that object using this formula. Okay, if I asked you a projectile motion question on the test, I will not have this formula on there. Okay, so you do need to know that. And you can make a reference sheet, so you can write it on your reference sheet. Okay, and that's our formula. It says the height of an object as a function of the time is equal to negative 16t squared plus v sub 0t plus s sub 0. Okay, v sub 0 is your initial velocity. In other words, how fast did you throw the object when you released it? S sub 0 is how high was the object off the ground when you released it. Okay, so for like somebody in baseball, that might be like 5 or 6 feet off the ground when they release it. Maybe closer to 5 feet. I don't know. Or are you on top of a building when you release it? Okay, that's your initial height. And we have to make sure with this formula we're using units of feet and seconds. Okay, if you take physics and you see this kind of formula, you might see the number 9.8 in place of the 16. Okay, that's because they're using meters per second. We use feet per second. Okay, so in the example we're going to do, it says that a rocket is shot straight up from ground level with an initial velocity of 64 feet per second. Okay, so I know 64 feet per second, that's initial velocity. What does ground level tell me?
It's at the ground.
Okay, it's at the ground, which means what's 0? The initial height. Okay, so ground level means initial height is 0. You're not even going to need it in this problem.
Shouldn't initial height, if it was truly 0, shouldn't that be sea level or something like that? Isn't that how everything's measured?
Well, it depends where you're measuring relative to. Like I could say right now, my pencil is 2 feet above the table. Maybe I'm measuring it relative to the table.
So they're measuring it relative to the ground.
To the ground, yes, where they are, yeah. Or I could also say my pencil is 1,000 feet above sea level right now. You know, depends what I'm measuring relative to. Okay, so this is level with the ground that they're at. Okay, I want to know at what time will the rocket be 50 feet above the ground? Okay, and remember, the rocket's going up, so at some point it's going to be above 50 feet, and then it's going to keep going, it's going to hit its maximum, and then it's going to start to come back down. So the rocket's going to be above 50 feet for a certain amount of time, maybe between 2 seconds and 3 seconds or something. Okay, that's what we're going to solve for. All right, so let's fill everything in our equation. Negative 16t squared plus v sub 0t. What's the initial velocity here?
64 feet.
Yep, 64 feet per second plus s sub 0. What's my initial height?
Nothing.
Nothing. Okay, ground level. Okay, and they want to know when the rocket is how high? 50 feet. That's your height right there. Your height as a function of time. Now I could solve this problem just like we did the last one. This is a quadratic. Bring everything to one side, use your quadratic formula. Okay, this time I'm just going to do it graphically. Okay, and the way I'm going to do it is take what's on the left, plug that into y1, 50. Okay. Take what's on the right, plug that into y2. Okay, so a little bit different than getting it equal to 0. I could if I wanted. I could do this just the same way I did the calculator last time. I don't want to this time. Okay, so I'm plugging 50 in y1, negative 16x squared plus 64x. You do need to use x as the variable in the calculator. You can't use t. So x is how long it's in the air for. Y is how high it's going to go. Well, I don't know the maximum height this object is going to hit. So I'm just, I'll guess 90 feet. If it goes off the screen, I'll fix it. Okay, but what I do know is it's not going to go underground. So set your y min at 0. And x is time. So when you're dealing with time, what kind of numbers make sense? Right, you can't go backwards. Okay, now back to the future. Okay, so until we get the flux capacitor, our time has to be 0. Time x max is how long the object is in the air for. I don't know. I'm going to guess it's in the air less than 8 seconds. If it's not, it's going to go off the screen. Okay, so there's my height at 50. There's the path of my object. That's fine. Yep. So we can see there's a certain time when this object is above the blue line, okay, above 50. Anybody remember what I need to calculate to find this and that? I need to find those 2 points. How about, Nick, do you remember how to find those?
You use the second calc.
Yeah, second calc.
And I'm lost from there.
All right, anyone help him from there? So we got a good start. Second calc.
Well,
Yep.
intersect.
Yeah, intersect. All right, so I'm going to move my cursor. I'm going to do the one on the right. If someone else can do the one on the left, that would be helpful. But pick a point somewhere on the first curve. Pick a point somewhere on the second curve. Hit enter. And now it matters where you put the guess. Wherever you put the guess closer to, that's the point it'll give you. So I'm putting my guess closer to the one on the right. So on the way back down, at about 2.94 seconds, the object is at 50 feet. and then after that it drops below 50 feet. Okay, so if you want the object above 50 feet, your time has to be between 2.94 seconds, has to be less than or equal to that, but it also has to be greater than or equal to, anybody get that other intersection? 1.06. Anybody else get 1.06? Yep. That's the time when the object is above 50 feet. Okay, and the last question says, what is the maximum height and when is the maximum height reached? Yeah?
For the intersection on the left, would you want it to be the number by the x or by the y?
It's the x. X is
Okay.
time, y is height.
Okay.
Okay, yep. So now I want to find a maximum height. Okay, it's another function under the same menu we just used. Anybody have a guess what function I'm going to use this time?
The max and min height, like that's in second calc.
Yeah, we're going to calculate a maximum. Second calc
Yeah.
maximum. Okay, the way you do this one is you got to pick a point. Well, first of all, I'm on the wrong graph. I don't want to be on the line. I want to be on the parabola. So I hit my up arrow, so now I'm on the thing that I want to deal with. Pick a point somewhere to the left of your maximum, hit enter. Okay, pick a point somewhere to the right, hit enter. There's only one maximum in between those two dotted lines, so the guess doesn't really matter. But it says the maximum is at about how many seconds if we round that off? 2. Okay, if it says 1 point and a bunch of nines, it probably should just be 2. Okay, so what is the maximum height? And when does it occur? Let's just take, so 64 feet is the maximum height. Max height. And this occurs when? At 2 seconds. Okay, any questions on that? All right, so the last thing we're going to look at in this section, and then we'll do a quick review of slope and that kind of stuff, is what's called a piecewise function. Okay, and basically what a piecewise function is it's graphing two functions at the same time. Okay, a little differently than what we did before, and I'll show you. Okay, you're splitting up the domain into parts. So basically you're saying, okay, I'm going to give you two different formulas to use for my graph. I'm going to say use this formula if x is less than 1. I want you to use a different formula anytime you're greater than or equal to 1. Right, so you can split it up. This is split up into 2 parts. I could split it up into 3 parts. I could say if you're less than 0, do this. If you're equal to 0, do this. If you're greater than 0, do that. Right? So you're just basically telling somebody when to use which formula. And you only use these formulas under the conditions written down. Okay, so in the example I have, if I said to you, I want you to plug in -4. Would you plug -4 into the top formula or the bottom? Yeah, you're supposed to use the top formula for any numbers less than 1. So if I said plug in -4, who cares about the bottom formula? It has nothing to do with that number. Okay, what if I said to plug in 10. You'd plug 10 into the bottom. Okay, so it's almost like we're taking two different graphs and we're just going to put them together on the same screen. And I think the trickiest thing is how do you graph it? Okay, so I'm going to show you how you do it on the calculator. Right, so the key to graphing a piecewise function on the calculator is parentheses. We've got to put everything in parentheses. Normally when we graph a function, we don't have to. Okay, but now we will. I'm going to type the first one in y1, 3 minus x squared. But now I only want it to graph that when x is less than 1. So next to it, I have to type in the condition, x less than 1. Okay. So again, put a parenthesis, put x, and now we need to find the less than sign. Okay, I'm going to show you where less than is. It's under second math. Okay, it says test right above it. If you press second and math, you'll see all your inequality symbols. Okay, I want less than 1. And now do the same thing for the second one. In parentheses, type x cubed minus 4x. If you don't put parentheses, it just won't work. Okay? Parenthesis, x, and now I want greater than or equal to 1. So press second, math, fourth option down, greater than or equal to 1. And what's nice is this is going to be two different colors, at least on mine, so you'll be able to see clearly which one is which. Yeah, and I'm going to do a standard window. I'm going to do zoom 6. Okay, so you know what I'll do? I'll leave this here so you can see how I did it. Do zoom 6. And let's see. So notice all of a sudden the parabola just stops. Ignore the parts that are on the x-axis. The calculator doesn't know what to do then. Okay? So, oops. Let's see if I can try to get this picture for you. There we go. All right. So that's pretty much what it should look like, except it should not be drawing any colors on the x-axis. So it should look like that, okay, up to that point. And notice here, are we including 1 or are we strictly less than 1? We're less than 1. So we're not including it. So technically there should be a little open circle on the end. Calculator can't do that. And then what about in this one? Are we including 1 or are we strictly greater than 1? This time we're including it. So including 1 up. That's how a piecewise function looks. So a lot of times piecewise functions aren't connected. They're two separate pieces. So the first part is a parabola, and then the second part is a cubic function on from there. Okay, so any questions on how to type that in? And that's it. I think that's the last new thing today. So now we're just going to do a quick little review of some basic stuff. Okay, questions before I move on from piecewise functions? All right. If you ever had a third condition, just type it in on y3, just like we did the first two. Okay? But usually piecewise functions have two conditions. All right, so last thing we're going to look at is basics on lines, okay, linear functions. Okay, and we'll do a little bit of graphing when we do our last problem, which is a linear inequality. Okay, so y equals mx plus b. That's called the slope-intercept form of a line. Okay, if you already know that, you don't need to write it down. If you don't, I would. Okay, does anybody remember what M stands for? Slope. And how about B?
The y-intercept.
Y-intercept. What is a y-intercept? What does that mean?
Before where x is 0.
Exactly. It's where x is 0. It's where it crosses the y-axis. Okay. So anything that can be written in the form y equals mx plus b is called a linear function. Okay, notice there's no exponents on the x. It's not like it's x squared. If you do that, you get a parabola shape. Okay, if it's just y equals mx plus b, it's a linear function. Okay, and in our book, they add this extra condition. I'm just going to explain what this is, basically because of the symbols in it. They're saying that the slope and the y-intercept can be any real number that you want. The slope and the y-intercept are elements of the real numbers. Okay, so slope and y-intercept, any real number you want. The only number the slope can't be is 0. It's not that you can't graph it if the slope is 0. It's just that it's not called a linear function. If the slope is 0, we call that a constant function. It's a little different. Okay, so don't write down this whole word problem. There's really only 4 numbers, or even 3 numbers you really need to write down. Okay, so it's saying a house was purchased 10 years ago for $60,000. And now the house is worth $85,000. So 10 years later, the value of the house went up to $85,000. We're going to assume that there's a linear connection between the value of the house and time. In other words, the value of the house did this. It just went straight up. That usually doesn't happen. Usually home prices, are all over the place. Okay, but we're just going to assume the value of the house went straight up. I want to find an equation that models this situation. And then once I do, I want to know at what point in time was the house worth $71,250. All right, so if I think of money and time, okay, think of them as a coordinate. We talked a little bit about your independent and dependent variable. Which one here is the independent? Is it money or time? Independent. Time is independent, right? Okay? The value of the house depends on time. Depends on what year you want to look at. So at one point in time, let's say before any time went by at all, what was the house worth at the very beginning? $60,000. And then 10 years later, okay, when the time was at 10, what was the house worth then? $85,000. So there's my 2 things that I need to find the equation. I want to write it in this form. One of those 2 things, either the m or the b, I already know. Just from one of these coordinates.
You already know the
Yep, I already know b. What is b, Adrian? Yeah, B is 60,000. Okay, so I know that. But I need M. What's M stand for again? Slope. Okay, so to find slope, we have a formula. Sometimes we call it rise over run, or if you have coordinates, the way you find it, it's the difference in the y's divided by the difference in the x's. All right, so I'm going to use that formula, give myself a little bit of room, and I'm going to find the slope between these 2 points. Okay, y2 minus y1 over x2 minus x1. So 85,000 take away 60,000 leaves me with 25,000. 10 take away 0 leaves me with 10. What's 25,000 divided by 10? 2,500. That's my slope. Okay, so now fill in M and B into the formula y equals mx plus b. Y equals 2,500x plus 60,000. So what this 2,500 represents is every year that goes by, the house is gaining $2,500 in value. That's my rate of change in the value of the house. So we found an equation that says when the house was worth, or we found an equation for the house. Now they want to know when it was worth $71,250. So we'd have to plug that in somewhere. Would we plug it in for x or y? Y. X is time. We plug it in for y. And now just solve for x. Okay, just a simple two-step equation. Subtract the 60,000. Leaves me with 11,250. And what's my last step to get x by itself? Yep, divide by 2,500. Yeah, just 2,500. And once I do that calculation, I will know at what point in time the house was worth the amount of money they're asking me for. So 11,250. So about 4.5 years after it was purchased. If you didn't want to solve it algebraically, we could have done this graphically as well. Put this in y1, put all of that in y2, and find where they intersect, and you'd get the same answer. Okay, I'm not going to do the graph this time. Okay, there's two lines that have special slopes. Does anybody remember what the slope of a horizontal line is? Yep, it's perfectly flat. Okay, horizontal line, slope is 0. How about a vertical line? Yes? Okay, it is. It's almost like it's infinitely steep. Does anybody know what we normally say? I guess you could say it's like infinite, but it's usually a different word we use. Yeah? Undefined. Okay, and because horizontal and vertical lines are special cases with slope, they're also special cases when we write the equations of them. They're not quite y equals mx plus b. A little different. If you have a horizontal line, the equation of it is just y equals, and then a number, 2. Okay, I can graph that on the calculator. Horizontal line, no problem. Equation of a vertical line is something like x equals -8. That I cannot graph on the calculator. Okay, so these are kind of special cases. They're not y equals mx plus b. It's just y equals a number or x equals a number. So I want to know the equation of, let's start with the horizontal line. So y equals. What would be the horizontal line that would go right through the point 2, 3? Let's think about right 2 up 3. I want to know the equation of that line. It'd be y equals what? 3. And y equals 3. Okay. And now I want to know the equation of the vertical line. Yeah, it would be x equals 2. Okay. That's it. Any questions on that? Okay. Let's say I had something written like this. 2x plus 3y equals 6. Can anybody tell me what I would do to make it look more like that? Yep, Nick.
You subtract the 2x.
All right. And instead of writing it as 6 minus 2x, I am going to subtract it, but I'm going to write it as negative 2x plus 6. And what would be my last step? Yeah, and then divide by 3. So that would be y equals negative 2/3 x plus 2. Why might you want to do that? What's the advantage of changing it from this into what's up above? Yep.
Because you're going to be giving your y-intercept.
Okay, now you get the y-intercept directly. I can see it. What else can I see directly that I couldn't see before?
I think you could find like a certain point on the line, on the line you're like because you're using a vertical and a horizontal intercept, right? That's what you're trying to do. You're trying to find like one point on the line.
Well, what about this? What does that tell me?
It's negative 2/3
And what is that number? That's my
x intercept or slope.
slope. That's my slope. Okay, now if I've rewritten it like this, I can see my slope, and it does get into the graphing. It tells me from the y-intercept, okay, if I wanted to make a graph of this, all I have to do is get a piece of graph paper, graph my y-intercept at 2, and now go down 2 and right 3. Down 2, right 3. You can do it again if you want. Draw a line, and there's your picture. Makes it quick to graph. Okay? Whereas in this form, not so quick. Okay, another form of the equation of a line instead of slope-intercept is called point slope. Okay, we don't use point slope as much, but it is used. And it's very helpful if they give you a point and a slope and you want to find the equation of a line. Okay, and the formula is y minus y1 equals m times x minus x1. Okay, and I'm going to use that formula to answer example 3. It says find the equation of the line that has a slope of a half and it goes through the point negative 2, 3. Okay, what I'm using right now, you don't have to. You can go back and use y equals mx plus b. But the problem is I don't know b. So I'm going to have to find it. This way, I don't have to find b. I can when I'm done, but I don't have to. Okay? So what would I fill in for y1 in this case? 3. Yep. What would I fill in for m? A half? And lastly, what would I fill in? Well, what would I fill in for x1 and what's going to happen when I do that? Yep. When I plug in -2 for x1, I'm subtracting -2. So as Ian just said, it becomes a +2. That's it. That's your equation in point slope form. If you don't like it in point slope, you can rewrite it in y equals mx plus b just by doing this. You can distribute the 1/2 and then add 3. Okay, so both of these answers are correct. It just depends on what format you would like it in. Okay, sometimes they even write it in what's called general form. I don't want to spend too much time on that. But does anybody see what I could multiply everything by here, and it would get rid of all my fractions in that problem? Yep.
What happened? You could multiply times 2.
Yeah, multiply it by 2. Okay, and watch what happens. You get 2y equals x plus 8. And sometimes what they do is they move everything to one side. So let's just go like this. 2y minus x minus 8 equals 0. That's a third way to write the equation of a line. That's called general form. When you get 0 on one side and generally no fractions on the left. Okay, I stick with this one. I like this one a lot. And I'll use this one sometimes, but not as much. This one I almost never use. But just in case you ever like check your answer and they have this for an answer and you got that above it, same thing. Okay, what do we know about parallel lines? Parallel lines have the same what?
Slope.
Same slope and different. Because if you just had two lines with, say, the same slope and the same something else, they would be the same line. But it's got to have a different y-intercept. Same slope, different y-intercept. Does anybody remember what the rule is for perpendicular lines? The slopes are opposite, reciprocal. Okay, so an example of that, if you had something with a slope of 2/3, you take the opposite, make it negative, and flip it. Those two numbers are opposite reciprocals. All right, so if they ask me to write an equation of a line that's parallel to 3x minus 2i equals 1 and passes through the point 1, -2. Well, I'm thinking I'd like to use point slope form because I have a point. But look at 3x minus 2i equals 1. What can I tell easily by looking at that? Something that I need to know about this line. If you want me to find an equation that's parallel to that, what do I need to know? Yeah, I got to know the slope. So if you want something parallel to this, the first thing I need to do is find the slope. And my line is going to have the same slope to be parallel. Quick way to find the slope? Just get y by itself. Okay, so bring the 3x to the other side. And lastly, divide through by, careful, not 2. Yeah, -2. Okay, we don't even really need to finish it as long as you can tell me what's my slope. Yep. So now the problem is write an equation of a line that has a slope of 3/2 and passes through the point 1, -2. We just did a problem like that on the other page. There's your slope. There's your point. What if I said perpendicular? what would you do with the 3 over 2? What would you make it?
Negative 2 over 3.
Negative 2 over 3. Okay? So I'm not going to finish it up from there because we just did one like that. I think the last thing we'll look at is how we shade something in on a graph. Yeah, that's our last problem. Okay, so when we're graphing a linear inequality, okay, the only difference between graphing a linear inequality and graphing a line is that you have to shade either above or below. Okay, and when you draw your line can either be a solid line or a dotted line. Well, if you ever see the symbol less than or equal to or greater than or equal to, you use a solid line. If you see the symbol less than or greater than, you use a dotted line. Okay, and how do you know when to shade above or below? Less than or equal to? Think less than. Less than is lower, right? Below. If you ever have a greater than, okay, or a greater than or equal to, think greater is higher, right? Shade above. Okay, so using these two rules, it'll tell us when we need to shade above or below, and whether it's a solid or a dotted line. Okay, really quick, I'm going to graph this line. I'm going to do something I've done a bunch of times. I'm just going to get y by itself. All right, is this going to be a solid line or a dotted line?
Solid, dotted.
Dotted. Okay, my y-intercept, it's a little messy, 4/3 is 1.3. Estimated. And my slope says go down 2, right 3. Down 2, right 3. Down 2, right 3. And I'm going to put in dotted line. And would I shade above or shade below?
Shade below.
This is a less than. Shade below. Okay, we went through that one a little quick, so if we need more time tomorrow, we can do another one of those. Okay, so homework tonight on page 31. Okay, try 32 to 36, 45, 50 to 52, and 55 to 57. And then on 42, it just kind of skips around to a couple different problems. 2, 8, 11, 16, 17, 20, 24, 27, and 32, 34, 77. Okay, so we'll look at that first thing tomorrow, and then we'll go down, get the Chromebooks at 8:50, and we'll come back up. And tomorrow, the material might be a little newer, so I think we're just going to stick with one section tomorrow.